I've been thinking about pangrams, which has led me to some interesting insights on data structures and computer algorithms, so I thought I'd share what I found. If you don't know much about these subjects, don't worry. The core concepts I'm going to talk about should be accessible to just about anyone. So what is a pangram? A pangram is a sentence with every letter of the alphabet at least once. These are commonly used to demonstrate the letters in a typeface or font. The most widely known pangram is this one. This has 33 letters, which, to me, begs the question, can we find something shorter? Naturally, many others have had the same thought, and the holy grail would be to find a perfect pangram, a valid English sentence with every letter exactly once. So, being a computer programmer, I immediately started planning a program to search for this holy grail. First, to get a sense of the scale of this problem, let's look at some numbers. The English language is estimated to have over 1 million words, but most of them are so obscure that hardly anyone knows them. Dictionaries and other curated word lists often have closer to 100,000 words, so we'll use that for now. If you include Y, there are 6 vowels in the English alphabet. So overall, we have an average of about 3 consonants for each vowel. The easiest way to achieve that ratio is probably to have 1 vowel per word, so we can guess that a perfect pangram will likely have about 6 words. The number of combinations of 6 words from a collection of 100,000 would be written as 100,000 choose 6 in math notation. This works out to about 1 octillion, or a billion billion billion. Even if we could work out a way to check 1 million of those combinations per second, a modern computer would take about 40 billion years to try all of them. Clearly, this just try all of them strategy isn't viable. I think the first obvious way to narrow this down would be to throw out all the words with repeated letters. Words like apple can't possibly be in a perfect pangram since P appears more than once just in this word. It turns out around 80% of English words have duplicate letters, so let's revise our estimate. 20,000 choose 6 is still something like 88,000 billion billion, which would still be around 2 million years. This is a huge step in the right direction, but clearly we need to do better if we ever want to see the results of our search. One thing that can help us spot ways to improve this kind of search is to look at some concrete examples. If we create a simple program to read a list of words, filter out the ones with duplicated letters, and then output the first set of 6 words, we get this. Oh, wow, yeah, that's a really bad guess. All 6 of these words start with AB. Obviously, once we choose one word that starts with A, we can at least skip down to the ones that start with B for the next word. In the case of these particular words, we could skip straight to C or even F for these last 3. There are several ways we could tell the computer how to skip forward, but I've chosen to split up our word lists into separate lists for each letter. Something like this. That's better, but this still isn't that good. Almost all the early words in these lists have A as the second letter. If we start by choosing a word from the A list, we definitely don't need any of the words with an A anywhere else in the word. Let's change this around to avoid that problem. Instead of listing words by the first letter, we can list them according to which letters appear anywhere in the word. Now that we have all the words containing A in this first list, we can take them out of all the other lists without any risk of overlooking a word that has an A somewhere other than at the beginning. Likewise, we could take the words with B out of the C list, and so on. If we do this for all the lists, we get back to having each word appear once in these lists. This looks promising. I can see that there's another easy improvement we can make. Anagrams are redundant for the purpose of this search. Removing all the anagram duplicates reduces the length of the lists by about 20%. Alright, now how do we use these lists to find a perfect pangram? It's pretty simple. All the words with an A are in this first list, so we definitely need exactly one of those. After choosing a word from the A list, we can move to the next lists, skipping over any list with letters we already have. The next list for a letter we don't have will include all the remaining words which have that letter. Therefore, once again, we need to choose exactly one word from that list, with the provision that it can't have any letters in common with our first word. Next, we can continue to the rest of the lists in the same fashion until we find an answer, or until we find ourselves left with a set of letters that can't be made into words. Every time we hit a dead end like that, we can backtrack and choose a different word from an earlier list. Of course, most combinations will turn out to be dead ends, but still, this should be a lot faster than the millions of years it was going to take from blindly trying every combination. Because we can't know in advance how many lists we will be able to skip or how many dead ends we will run into, the exact time to execute this refined approach will be hard to predict. Based on some rough estimates and small tests, I think this should probably take a few weeks to find every perfect pangram. Yeah, that's probably fast enough that I could just let it run on my computer and check every day or so to see if it is finished. So I wrote a small program to follow this algorithm and set it working. While that was crunching away in the background, I had plenty of time to think about more ways to speed this up. Splitting the full list up into smaller lists based on the letters in the word definitely made it possible to have the computer skip a lot of words it didn't need to look at, but it's still looking at plenty of words that aren't going to work. We should be able to repeat that trick of splitting up the list so the computer can know how to skip more words. For example, if we take the list for B, we can split that into smaller sublists based on the other letters in each word. This way, if we were looking for a word with B but not C or D, we could skip these sublists for C and D. Within these sublists, we could split them again, and so on until there is nothing left to split up. If we do that with all the lists, all the way down, we end up with a tree something like this. The full tree would have many thousands of branches, so I can only show a small part of it at a time. Okay, we have this tree of letters, but where did all the words go? Let's take a word and see how it would be represented in this tree. If we sort the letters in idea, we get A, D, E, I. So the first letter we'll consider is A. That tells us to start with the trunk for A. The next sorted letter is D, so under the A trunk we need to go down the branch for D. Under D, we need to go down the branch for E, and finally, under that, we take the branch for I. At this point in the tree, we find a leaf that is labeled with the word idea. Note that just because there is a word leaf at this point doesn't mean that there can't be more branches connected from here. In this case, there would be at least one more branch below this with S, where we would find a leaf labeled ideas. We would also have passed a leaf on the way down for the word add, since that is made from the alphabetically early letters in idea. So how can we use this tree to find a perfect pangram? To choose our first word, we would just work our way down the A trunk and choose any word leaf for our first word. For the next word, we know that all the words connected to the A trunk have an A, so we can move on to the next trunk for a letter we don't have yet, just like we did with the lists. However, under that next trunk, we will be presented with a choice of branches for the alphabetically next letter. Any of those branches labeled with a letter we already have in the first word can be ignored, since all the words down that branch will definitely repeat a letter in our first word. We can travel down any of the remaining branches to find a word leaf to select as our second word. This can be repeated on the other branches as many times as needed until we either have a perfect pangram or hit a dead end, which is the more likely outcome if we start with a vowel-heavy word like idea. Being able to rule out entire sets of dozens or hundreds of similar words just by checking a single label on the branch they are attached to has the potential to really speed up this search. Writing a program that can correctly construct and navigate this tree is a bit harder, but with a clear picture of the concept, it is certainly doable. If we run this program, it starts spitting out perfect pangrams after just a few minutes. It takes about 15 hours for it to finish searching for every perfect pangram. For the list of words I've been using, it finds 1,919 results once you factor in the anagrams. In no particular order, here are some of the perfect pangrams it found. These words are still sorted in the order the program picked them, and we haven't considered the rules of grammar yet, so these aren't actually sentences. They also seem to have a lot of obscure words. In fact, every one of the 1,919 pangrams have at least one word I have never heard of, and there are about 100 results that are composed entirely of words I don't know, like this one. To save you some trouble, here are the definitions of some of the words along with how frequently they appear in the pangrams. It turns out that about 2/3 of the pangrams this program found contained 7 words, about a third had 8 words, and only a few had 6 words. Now we have our answers, but I'm still not satisfied with how long it took the program to find them. I can still see a few things we can do to speed this up even more. Another good thing to consider when looking for ways to optimize a procedure like this is to think of how you would approach the problem if you were going to do it yourself. In this case, if I were going to search for a perfect pangram with a pencil and paper and a dictionary, I would start with the rare troublesome letters like Q, Z, and X. Intuitively, it seems like it should reduce the number of dead ends, where you're left with an odd assortment of hard-to-use letters that can't be made into words. Most of these difficult letters are way at the end of the alphabet, so right now the program is pretty much considering those last. According to various online sources, this is the alphabet sorted from least to most common letter in English. Let's build our tree with this order and give that a try. Nice! That cut down the time to a couple minutes. Our intuition about starting with uncommon letters appears to be correct. That's a 99.8% reduction in the number of word combinations it tried, which means that we avoided a bunch of dead ends. But this has the letters sorted by how common the letters are in natural text, not our narrowed list of words, so we can probably tweak that by sorting the alphabet according to a survey of the words just in our list. Adding a step at the beginning of the program to work out this optimized alphabet gives us a somewhat different order. Then, if we run the full program with this analyze and sorting step included, the time and number of word combinations both get cut in half. Oh, almost got it down to a minute. Can we find another way to improve this? Yes, we can. Up to this point, the tree navigation code that is searching for word combinations has been using a list of remaining letters to keep track of which letters we still need to find. This works fine, but computers are just a big fancy pile of math disguised as other stuff, so if we can find a way to make this into more of a math problem, the computer should have an easier time doing the work. Fortunately, there is a way to represent this set of remaining letters as a single binary number like this. If we want to represent the letters S, I, M, P, L, E, then we just set the bits in the corresponding column for each of those letters to 1 and all the others to 0. Computers store numbers in binary, so storing and manipulating the set of letters we are looking for like this turns out to be easy and fast, for a computer anyway. The inspiration for this last idea goes to Fred Overflow. The link to his video where he uses this bit flag representation trick to solve another similar problem is in the description below. After updating the program to use this trick, we can see that it now finishes in less than 9 seconds. Amazing! Starting with a problem that would probably take billions of years to solve, we found clever ways to filter and arrange the data until the solution could be computed in seconds. I hope this illustrates what an important role choosing your data structure can play in answering questions about a large data set. A data structure tailored to the situation can sometimes make a nearly insurmountable computation look almost trivial. On a technical note, I used a recursive algorithm to traverse this tree, and I've never been any good at figuring out the big O notation for the performance of a recursive algorithm, so I'm not actually sure what that would work out to for this algorithm. I'm guessing it's something like n cubed in the average case. If any of you can work that out properly, I'd love to see it in the comments. Another detail I skimmed over is that none of these pangrams have been arranged in a way that forms a grammatically correct sentence. I haven't been able to find any significant lists of words annotated with which part of speech they are, and without that there wouldn't be any way for a computer to know which word orders might be valid. I'd love to tackle that problem, so if any of you find the data needed, please let me know. As I was wrapping up production for this video, I found that someone else has also run a search for these perfect pangrams. They used a completely different method and a different dictionary, so their results aren't quite the same. Their program was really clever, but not quite as fast as this one, I think. A link to their article explaining it is in the description. If you'd like to see my code for this or a complete list of the results, the links for those are also down in the description. Thanks for watching.